Graphical methods are another means of describing the behavior of data. We have a host of methods in which to understand the distribution of a data set. Graphical methods includes box plots, stem and leaf plots, scatter diagrams, run charts, histograms, and normal probability plots. A frequency distribution groups data among several categories, or classes. By listing the classes and the frequency, or number, of data values in each class. Classes are the same width, or size. There can be no overlap or gaps between classes. Each value must fall in one and only one class. Frequency distributions are tabular, but a great starting point if we wish to create a histogram. Histograms are visuals created from frequency distributions. A histogram is an approximation of the distribution's shape. Like frequency distributions, there are many valid histograms that can be created for a given set of data. Our goal in creating histograms is to uncover a normal, or at least a known, distributive behavior. This requires us to adjust the size of our classes and the number of classes. These two parameters compete against each other. As we raise the number of classes, the width of each class gets smaller. As we lower the number of classes, the width of each class gets larger. Clearly, finding the sweet spot can be time-consuming without technology. Histograms require a minimum of 50 to 100 data points. Histograms can also tell us about the stability of the process. Going into a project, we must first have a stable and predictable process. Otherwise, our investigation will yield invalid results. A stable process is frequently characterized by a histogram exhibiting a unimodal or bell-shaped behavior. An unstable process is often characterized by a histogram that does not exhibit a bell-shaped behavior. Stable processes are easier to work with when it comes to identifying and localizing sources of special cause variation. Every process has a certain amount of healthy variation, called common cause variation. We never want to reduce common cause variation. Instead, we wish to go after assignable or special cause variation. The box plot is the 5-number summary of the data. The top and bottom sides of the blue box are Q3 and Q1 respectively. The red line is Q2. The horizontal lines at the end of each dotted line are the fences. Any value falling outside the interval between the lower and upper fence would be an outlier candidate. In this visual, the maximum and minimum values are indicated by the red pluses and could be possible outliers. Box plots are great tools for identifying potential outliers. Risk is an essential factor in making this determination. Risk is based on the multiplicative factor we use times the IQR to subtract from Q1 to get the lower fence and add to Q3 to get the upper fence. A liberal attitude toward risk is indicative of a factor of 1.5 times IQR. A conservative stance would require 3 times IQR. Studies have been done that in fact show that 1.5 IQR is too liberal. In other words, we are throwing out data we should be keeping. And 3 IQR is too conservative. In other words, we are keeping data that should be thrown out. Hoagland and Engelwitz investigated this phenomenon and found that a 2.2 IQR is the best factor for fence placement. As you can see in the right visual, when we overlap the 1.5 IQR box plot with the normal distribution, we see that the distance between Q1 and Q3 accounts for only 50% of the data. Normally, we would expect to see 68% of the data between plus or minus 1 standard deviation. The 1.5 IQR fences only reach to plus or minus 2.68 standard deviations. This is only 99.26% of the data. We will learn that at plus or minus 3 standard deviations, we see 99.7%. And this is grossly inadequate from a Six Sigma standpoint. A scatter diagram is a graph of XY pairs of data. We seek to uncover a relationship between X and Y. Scatter diagrams can help determine if a relationship exists, give an idea of the strength of the relationship, and indicate how to control the effect of the relationship on the process. The closer the data is confined about a best fit linear line, the stronger the linear relationship. Traditionally, the dependent variable is on the vertical axis and the independent variable is on the horizontal axis. It is important to note that correlation does not imply causation. This is a common misstep in statistical analysis. Not all scatter diagrams reveal a linear relationship. We could indeed uncover a nonlinear yet known relationship with a scatter plot. Use common sense when creating a scatter plot. The data must be paired. We are looking for meaningful relationships as opposed to nonsensical ones. There are, in fact, many things that are correlated, yet they lack a relationship. For example, the phone ringing every time you are in the shower. The human brain is not able to process many numbers at once. One way to assimilate large amounts of data is with a runs chart. Run charts plot trends and show patterns that indicate if a process is running normally or whether desirable or undesirable changes are occurring. In a later segment of this specialization, we will be spending more time on the many types of run charts and how to interpret them. The stem and leaf diagram is a very useful and informative way to plot data sets. They closely mimic the behavior of a histogram. Unlike a histogram, though, we can uncover additional detail about the dispersion and central tendency of the data within each stem. Stem and leaf can be used for variable and categorical data sets. The class intervals are the stems, and the data within each stem is the leaves.